My name is Sabrina Vantadori, and the paper that I'd like to present you today is entitled Lifetime Estimation of 360 Stainless Steel Specimens by using a critical plane approach. The goal of the present paper is to evaluate the lifetime of 360 stainless steel specimens subjected to high cycle fatigue multi-axial loading by using the multi-axial critical plane-based criterion proposed by Carpinteri et al. Although the criterion has already been applied to many data available in the literature, both in terms of different materials and loading conditions, the novelty of this paper is its application for the first time to simulate finite life experimental tests performed under high cycle fatigue regime and consisting in loading conditions involving axial loading and internal pressure. More precisely, my presentation consists of the following sections: introduction, description of the Carpinteri et al. Criterion, description of the experimental campaign examined, presentation of the results obtained and discussion, and final conclusions. In the last 20 years, the criterion by Carpinteri et al. Has been widely used to simulate many experimental multi-axial fatigue tests available in the literature, both in the case of infinite life tests, some publications of the authors are here shown, and in the case of finite life ones and some case study too. Summarizing the works done up to now in the table here shown, where B stands for bending, T stands for torsion, A stands for axial loading, where the subscript R represents the loading ratio and P stands for inner pressure, it can be observed that the table is quite filled on the left-hand side, but quite empty on the right-hand side. By grouping all still examined up to now in a unique group, the table on the bottom highlights that a verification of the accuracy of the criterion is needed for those loading conditions involving axial loading and inner pressure. Therefore, in the present paper, these loading conditions are analyzed, coming the examine experimental data from tests performed in Japan by some of the present authors, as is detailed in the following. The Carpinteri et al. Criterion here employed is a high cycle multi-axial fatigue criterion falling in the category of the stress-based criteria. The fatigue damage parameter adopted is an equivalent uniaxial stress, defined as a combination of the stress vector components acting on the critical plane. The critical plane is assumed to be correlated with the principal stress direction. The main steps of the criterion apply to a multi-axial constant amplitude cyclic loading are hereafter described. Firstly, the critical plane has to be determined. Let us consider a generic material point P and fixed frame XYZ with its origin in P. At a given time instant T, the principal stress directions 1, 2, and 3 can be defined through the principal Euler angles phi, theta, and psi. The mean principal stress directions are defined by averaging the instantaneous values of such angles as is reported on the right-hand side. By assuming the weight function W here reported on the bottom, the average principal stress axis, namely in the following 1 week up, 2 week up, and 3 week up, coincide with the instantaneous ones at the time instant when sigma 1 achieves its maximum value during the period. The normal vector W to the critical plane is obtained through a rotation delta of the 1 week up direction in the average principal plane 1 week up, 3 week up. The off-angle delta is expressed as follows, where sigma f minus 1 and tau f minus 1 are the fatigue strength at a given number of loading cycles, generally assumed equal to 2000 cycles, for fully reversed normal stress and fully reversed shear stress, respectively. At each time instant t, the stress vector SW related to the above critical plane orientation may be decomposed in two components, that is, the normal stress vector n and the shear stress vector c, perpendicular to n line on the critical plane, respectively. During the period t, the direction of the normal stress vector n is fixed with respect to time, whereas the shear stress vector c describes a closed path sigma on the critical plane. The criterion proposes to transform the actual multi-axial stress state into an equivalent uniaxial one by means of the expression here shown. The equivalent normal stress amplitude NEQA is based on the well-known linear interaction between the normal stress amplitude and the normal stress mean value, described by the diagram of Goodman. Such an equivalent amplitude is introduced in order to take into account that a tensile mean stress superimposed upon an alternative normal stress strongly reduces the fatigue strength of metals. As is previously mentioned, the amplitude NA and the mean value NM can readily be computed since the direction of n is fixed with respect to time. On the other hand, the definition of amplitude CA is not unique. The present criterion implements the CA computation by means of the maximum rectangular hull method proposed by Araujo and others. The method considers rectangular hulls bounding the closed path sigma. Each rectangular hull is characterized by an orientation xc measured with respect to an arbitrary direction fixed with respect to time. We assume the u direction and by the rectangular side. For the rectangular hull with the orientation xc, the hull values of such sides can be computed as is reported in the equation on the left-hand side. According to the method, CA is defined as the shear stress amplitude value, which maximizes the equation reported on the right-hand side. Finally, according to the Carpinteri criterion, the number of loading cycles to failure and cal can be obtained from the iterative solution of the expression shown on the bottom. This expression is obtained from the critical condition 1, here reported again, by replacing the fatigue strength sigma f minus 1 and tau f minus 1 referred to 2000 cycles with the fatigue strengths at the finite life and cal by exploiting the Baskin expression both for fully reverse normal stress and for fully reverse shear stress. The criterion is here applied to some experimental high cycle fatigue tests performed in Japan by some of the present authors. The tests are characterized by constant amplitude loading performed on hollow cylindrical bone-shaped specimens made of 360 stainless steel and alternately subjected to axial loading, inner pressure push-pull, and the combination of axial loading and inner pressure. The testing machine used is an electric servo-control multi-axial fatigue testing machine. The actuator on the upper side is used to apply the inner pressure, whereas one of the two actuators on the lower side is used to apply axial loading. The failure life is defined as the number of loading cycles required to reduce the maximum inner pressure that result from the initiation of a through crack or rupture of the specimens. Therefore, under both axial and push-pull loading, a constant inner pressure of 1 megapascal is applied during test. The details of loading condition examined are shown here. In this figure, the experimental fatigue lives are compared with the calculated ones. The solid line indicates NCAL equal NEXP, or results above such a line are conservative. The dashed lines correspond to NCAL over NEXP equal to 0.5 and 2, and the dashed dot lines correspond to NCAL over NEXP equal 1 over 3 and 3. It can be observed that the results obtained are quite satisfactory for the fatigue loading condition being examined. As a matter of fact, 85% of the results fall within the scatter band 2, whereas 92% of the results fall within the scatter band 3. Moreover, almost 70% of the results are conservative. Therefore, for the loading condition here examined, the criterion provides results characterized by a quite satisfactory accuracy. And now let us move to the conclusions. In the present paper, the lifetime of 360 stainless steel specimens under high cycle fatigue multiaxial loading has been evaluated. Such an evaluation has been performed by using the multiaxial critical plane-based criterion proposed by Carpinteri et al. The novelty of the paper has been the application of the criterion for the first time to finite life experimental data involving axial loading and internal pressure. The results obtained have been quite satisfactory, with 85% of the results fall within the scatter band 2, whereas 92% of the results fall within the scatter band 3. All tough further verification are needed for different materials. Thank you for your kind attention.